And that would be the worst. Oh, and I have to remember to turn off the sound of my phone because you guys all laugh when it goes off. Okay. What does this graph need before we put anything on the graph? It needs some stuff. What does it need? It needs to have the axes labeled. Cost is what it is, and what's that measured in? Dollars. Excellent. What's on the bottom? Toppings. And that's measured in toppings. Now, we should assign variables, shouldn't we? Because this is the title, this is what it's measured in, but it's not the variable, is it? What's the variable we should use over here? You could use Y. But what would be better? What are we're measuring cost here, right? So what would be a better letter to use? C. What are we measuring down here? So what letter should we use? T for toppings. Excellent. Luke.
Because there's an independent variable, does it matter on which axis we label them?
The independent variable almost always goes on the x-axis, so you should have put it on the x-axis.
Okay.
Can I have 0 toppings on a pizza? Yes, because cheese doesn't count. Because if you don't put cheese on a pizza, you don't have pizza, you have bread. So that's 1, 2, 3, 4, 5, 6. If you go past 6, you have ruined your pizza. There's no need for more than 6 toppings on a pizza. And one of those toppings can never be pineapple, no matter what any of you people say. No, pineapple is disgusting. It has no place on pizza. No, stop it. Stop. No. Jalem, I love me some pineapple. I don't love me some pineapple on a pizza. No.
Is it the pizza that's ruining the pineapple?
It's the pineapple that's ruining the pizza. But pineapple, like pineapple, peel, great, spectacular, love it, can't get enough of it. Pineapple that comes out of crank. That's not pineapple. All right. What is the lowest amount of cost I could have? Right. So I could go ahead and put 12 right here, couldn't I? And 0 right here for time. Yeah? What kind of dot? Open or closed? Closed, because I can have a pizza with 0 toppings and there will be an output of $12. What's the next output? $13.50. So my first dot goes there. My next dot, $15. My next dot, $16.50. And I'm going to stop there because I'm out of room on my graph. Is it continuous or discrete data? It is discrete. Why?
Because you
can't have half a topping. If I say put pineapple on half because my class is crazy and likes Hawaiian pizzas, they'll still charge me. If you order a pizza online, you do that thing where now you can do it online. You can decide which half of the pizza has what. You guys seen that? If you go to like Papa John's and you want a half on it, you can even say which half gets it. So you can say half gets pineapple, half gets green peppers, and you can switch them. It's pretty cool. Except make sure you don't always do that online. Because if you say you only want half the pizza with pepperoni, for example, they will charge you for pepperoni, but they will not put on the full amount of pepperoni. Do you follow what I'm saying? If they're supposed to put on 20 slices of pepperoni and you say you want it on half, they'll put it on half. They'll only put on 10 slices of pepperoni, but charge you the full amount. You got to tell them, I want me all 20 slices of pepperoni, but only on half the pizza. I don't know. It depends on the formula. All those places, there's no art involved in. There's no art in working at any of those divey pizza joints. They have a formula. They know exactly how much of everything that goes on.
What if it's a traditional Italian place?
then there's some leeway and some latitude. All right, so it is not continuous, yes, because we cannot have half pizza. Is everybody cool? Everybody's good? Everybody has a graph that looks something like this, yeah? I noticed a few people are erasing. I'm assuming you were erasing your line. Some people made it continuous. No? All right, whatever. It doesn't matter. Now, you should be able to recognize a pattern here. Where's the next dot going to be? 18 on the y-axis, and what on the 4? So I'm going to go that way 1, and I'm going to go that way how far? 1.5, 150, right? Where's the next one going to be? Another 1 over and another 150 up, right? How long will that continue? Well, till you run out of toppings. No pizza joint has an infinite amount of toppings, although Panago used to. Almost infinite. You could get peaches on your pizza. I'm not lying. Canned peaches. You could get peaches on your pizza. You could get smoked oysters on your pizza. Back when Panago was called Panagopolis, they had a bazillion toppings. It was crazy. All right, so everyone's cool? Everybody's cool? Okay. This in red here is the important part, which is why I'm going to write the notes in red. A linear relation is one where the rate of change, which we've already talked about, right? The rate of change, I'm going to underline that because we have talked about it. What's the rate of change again?
1 to 150. I mean, 1 to 1.5. Is it the slope?
It is the slope. Kilometers per hour, right? That's a rate of change. That's speed, yeah? Yeah? Do not write it in the box. That's why I'm writing it here. I got something else to put down in the box.
Oh, is it 1.5 per topping?
Yes. So it is the rate of change, which is always the dV divided by the IV, the change in dV divided by the change in IV, where the rate of change is constant. Now that's weird to say a change is constant, right? Because constant means something stays the same. But in this case, what is staying the same is how much it is changing. Does everybody understand? That's why we can go over 1, up 1.5, and we can do that until we run out of toppings. Everybody cool? Okay, now, I'm going to write something in a different color because it's very important and people screw this up. What word do you see in the beginning of the word linear? Line. So every kid thinks that a linear relation must have a line. Must it? No. Oops. Linear relations need not be continuous. Okay, you can have a linear relation without drawing the line. Is everybody cool? All right, now, before we even talk about the bottom two, the next two spaces, I want to talk about what we have here. So far on this page, you have been given 2 ways to show a linear relation. What are they? Pardon? No, that's the kind of data it is. Right now on the screen, there are 2, Stephen. That's, again, the rate of change. I'm talking about the whole thing, the relation. Marley. Okay, you're getting warmer. I've asked the question poorly. I'm not asking you anything about math. I'm asking you, on this screen, right now, there are 2 ways to show or describe a linear relation, which is any relation between two variables. Joy. Well, that's the next two. They're not on the screen right now. I'm talking about the two that are on the screen right now. A graph is one. Linear relations can be represented by a graph. What's the other way that's on the screen right now? How did we draw the graph? Pardon? No. How did we put the graphs on the dot? The dots on the graph. Strike that. Reverse it. Why were we able to do that? The explanation. Linear relations can be on a graph. Linear relations can be words. You have to be able to work with all four of them. This is two of them. If you can make this graph from that sentence, you know how to work with two of them. The third one, as Joy has said, is a table of values, which you learned in the 9th grade. In the 9th grade, you learned it as X and Y. What did we change it to in the 10th grade? IV and DV. Who said that? Shut up. Nice job. Way to go. Yeah. Warm your hands on that fire. Warm your hands on that fire. Woo! We also had input and output, yeah? But IV, DV is what I'm looking for. In this case, what is the IV? What is the DV? IV is toppings, which we said was little t. DV was, which we said was big C. Yeah? 0 toppings, what's the cost? $12. 1 topping, what's the cost? $13.50. 2 topping, what it cost? $15. Everybody good? That's what you learned in grade 9. And then hopefully in grade 9, you learned how to take one of these, or a graph, or words, and create an equation. Some of you will have an issue with this. So we're going to talk about it right now. What is happening here? I'm adding 150. How long can I do that for? Till I run out of toppings. A lot of 150s, right? Especially if it's the 1990s and you're ordering from Panagopoulos Pizza. Now, you people understand math. What is the shortcut to doing plus 150, plus 150, plus 150, plus 150? Coefficient. 150 multiplied is the same as adding 150, yes? All right, now, if the cost is going up by 150 for every topping, then the 150 must be related to the toppings, correct? Because the toppings are the independent variable. So if I am adding 150 every time I put a topping on, what is that the same as? Let me write this out for you in a different way if you don't remember. First is definitely 12, yes? 0, 12. 1, I pay that 12 and I add 150, don't I? Right? 2, I pay that 12, I add 150, but now how many times? Twice. Everybody understand? Okay. 3, what do I pay? 12 plus 3, 150, correct? What if it is N? I lie, wrong letter. What if it is T toppings? Do I pay the 12? Yeah. Do I pay the 150? Yeah. How many times do I pay the 150? T. And there's the equation. Does everybody understand? Everybody cool? Notice that the 150 went with the T. That's a little shortcut that you can use if you wish. Right? Now, what if I said you can only order pizzas in toppings multiples of 2? Could I have this line here? No. So that line would be gone, wouldn't it? Right? Yeah? And if I had this line gone, right? Now, if I want to do an equation, I need to know what happens when I change my IV by how much? 1, right? Kilometers per hour. Yeah? So this has gone up by what? 2. This has gone up by how much? 3, correct? So the 3 would go with the toppings. Yeah? Everybody with me? So it'd be 3t plus 12 would equal, if the 3 goes with the toppings, where does the 2 go? With the cost. That's no good, is it? I don't want to know what double the cost is, do I? That does me no good, right? But I want to know what's going to happen here if I tidy this up, right? I need the rate of change. The rate of change that I have is 3 over 2, correct? Right? Because that's the rate of change I've been given, 3 over 2. Yeah? Well, what does 3 divided by 2 equal? No, it equals 1.5. And I get my single unit rate of change. Does everybody understand? Because we want our rates of change in the smallest unit we can get, right? We don't say we drove 180 kilometers in 4 hours, do we? Right? Think of that. If I told you I drove 180 kilometers, it took me 4 hours, and I asked you how fast I was going, you would not say, you're going 184 kilometers per 4 hours, Mr. Myers. What would you do to the 4? You would divide it by 4 to get it to 1 hour. What would you do to the 180? Divide it by 4 to get it to 180 divided by 4. 45. Thank you, Paul. Okay. Yeah, everybody. Ooh, that Paul, he's doing math in his head. I don't know. Maybe I should sit by him. 180 divided by 4. Everybody cool? All right, so now, in the box that everybody wanted to write in earlier, what we're going to write in there is the 4 ways that we can do a linear relation. 1, words. 2, graphs. 3, table of values, which some of you call a T-chart. 4, as an equation. Now remember, the equation is always dV equals IV and some math. Right? You're going to do some arithmetic to that IV to get your dV. Everybody got it? All right. Remember, it often helps the unit rate of change. And I'll give you that example. 180 km in 4 hours doesn't really help me. But if I can change that to 1 hour 45, now I'm in good shape. because that's the beginning of the math that is happening to my independent variable. Everybody cool? All right, I'll let that go for a second, then we're going to turn the page. When I hear a lot of pages turning, I'll carry on. What is a lot? That many. Hey, Stephen. The cumulative is marked. I do want to. We'll have to see. I think everyone has written it now. But, there's 3 that aren't marked. The last 3 that did it on Thursday, they're not marked. Okay. So, let's have a look at this. Celsius, Fahrenheit, yeah? So, let's change this to C and F. Everybody cool? Which is the independent variable? C. What is the dependent variable? Fahrenheit. F. Excellent. Now, let's have a look at the situation here. What is that going up by? 9. Excellent. I thought we'd have to go to Paul to solve that for us. Paul, you be ready to step in case the class can't figure out how much that's going up by.
Oh. I think I'm dyslexic, bro. That was a 3 like 1 second ago. I think I'm dyslexic. No, bro. Dude, that was like Yanni and then it turned to Laura. Bro, on me. That was a 3, bro. I need to get my eyes checked.
Yes, thank you. It is indeed 5. Now, does that really help us? No, it doesn't, does it? Right? But we're going to answer the first question first. Is it linear? Well, let's check. What did that one go up by? What did that one go up by? So, are the changes the same? Out 5, up 9, out 5, up 9. So is it linear? Yes, excellent. Step 1 taken care of. We know it. Step 2, let's make the equation. So, I right now know that I got to do 9 times C, don't I? Right? Right? Because the 9s are down here and the 9 goes with the independent variable. Because all the math has to happen to the independent variable, correct? But that 9 times C is going to equal 5 times F, isn't it? Does that help me?
No.
I don't need to know what happens when I move up 5 degrees. I need to know what happens when I move up how far? 1 degree. So how do I get that F to a 1 right now?
9
Divide by 5, divide by 5, right? Now, I have F equals 9 over 5C. Is everybody with me? Do I have an independent variable with some math? I do, don't I? Okay. What's the rule now? Let's check. When Celsius is 0, what would I write there? What would I write for C when Celsius is 0? 0. What's 9.5 times 0? 0. I need it to be 32. So what do I got to do here? I need more math. What do I got to do? I got to add 32. Everybody cool? All right, now let's check. When Celsius is 5, what would I write there? 5. What would happen to the 5 and the 5? Cancel, and I'd have 9 plus 32. Is that 41?
Oh, wow. That's cool.
So did it work?
Yeah.
We're done. Can everybody make an equation? There's lots of ways to figure it out. That's just the way I find it's easiest. What about this guy? Linear or not?
What the heck is that? It is not linear.
It's not. Why do you know that, Luke?
Well, 75 to 3,000 seem like a little bit.
The rate of change is not constant. Let's use English, or let's use mathematical terminology, right? Luke, you're absolutely right. 75 to 3,000 is way too big a jump. But that's not math, right?
Probably goes from 0 to 75.
Yeah, you're absolutely right. Yeah, but now let's turn it into math words, which are,
The rate of change is not constant.
this is nonlinear because the rate of change is not constant. Plus 75 plus 5 plus 5 plus 2,925. Right? Oops. That is no good. Everybody cool? All right. What about B? No, there's no factoring. This is a yes or no question. Is it linear?
Yes.
Joseph already knows. Luke says it's linear. Is it linear? Of course it is. Why do you know that?
Because even though we don't know the variable, each variable x or y will follow that equation.
Yes, absolutely. Whatever I do to x, you're going to double it and add 4. Right? So that is going to be linear. Oops, I don't want to write in red. Red's what I write when things are bad news. Linear. And you can prove it, x, y. Luke says we don't know the variables. So if we don't know the variables, what do? We pick some variables, right? 0, 4, 2, 8, 5. I don't want to do 5. 4, 12. Is it linear? Up by 2, up by 4, up by 2, up by 4. We're good, right? Okay, what about C?
Yeah. No.
Linear or not? If you're unsure, what can you do? Try it. What's 0 squared? Times 4? Minus 1? Negative 1. Okay. What's 1 squared? Times 4? Minus 1? 3. What's 2 squared? 4 times 4? 16. Minus 1? 15. Is that linear? Nope. No. Why, Luke? Hit me with it in math words.
Because the rate of change is not constant.
Why did you say it so nerdy and insulting like that? That's just hurtful.
So let's just move on.
Why is it hurting you? You just did it perfectly right. Check with Paul. D, yes or no?
No.
You guys all told me on the first page that you could do it from words, from a graph, from a table of values, and from an equation. That's a graph. You should be able to tell me, is that a linear graph?
Yeah.
Why do you say so, Jalem?
There's a line on it.
Well, Jalem, to be fair, that's a line. Is that linear? Probably not is correct. So, yes, there's a line. What makes it a linear relation?
It's because it's straight. It goes straight up and down, so it's like perfect, you know?
It doesn't go up and down. It's quite plainly diagonal.
It's continuous.
What is continuous?
The graph. The line goes
Continuous data? Well, this is continuous data. Is that linear?
No.
No.
I don't know how to explain it.
But you do know how to explain it because Harmon's already explained it once. Luke explained it in regular words. Then we said Luke used math words. Then he used math words. Then he made fun of me.
The rate of change is the same.
The rate of change is the same. Find a spot and check. When I go over 1, I go down 1 and a bit. Yes? So if I go over 1 to the left, how far should I go up?
Up in a bit.
1 and a bit. Did I? Is this distance the same as this distance? Yes. Is this distance the same as this distance? So, is the change in y, which is yellow, divided by the change in x, which is green, is it constant? Yes. So is it linear? Yes. What about e? Yes. Why?
Every time you go up by 1 on the x-axis, you go by 2 on the y-axis.
In e? Does your drawing look different from mine? I did say e.
Yeah.
So you said every time you go up by 1 on the x-axis, you go up by 2 on the y-axis. Dude,
Luke, it's gonna be a 2.
that's the line.
When it gets to 3, it's gonna be a 6. When it gets to 4, it's gonna be an 8.
No. Okay, you understand, right? Okay. So, Damaris. Yes, because something is still changing, isn't it? But it's change in y over change in x, right? So the change in x is what? X changes every time. +1, +1, +1, right? So x is changing. +1. What's y changing? 0. Is it always going to be that way? Yes. So that's linear because the rate of change is 0 over 1. Now you also know something. No, we're going to leave it there. Turn the page over to 187. Not linear. Why? Well, it's curvy. But in reality, why? The rate of change isn't constant. Because look what happens. From here to here, it barely goes up. But from here to here, it goes up a lot. So again, let's use real terminology. The rate of change isn't constant. What about G? Yes, because the linear is the rate of change is the same. All right. Did I give you guys graph paper? I did. Okay. Make a table of values and graph. We've already done this one. X, Y. What numbers, how many numbers do I need to prove if it is a straight line?
3.
I need 3 because I got to check on both sides, right? So any 3 numbers for an input. Choose 3 numbers.
1, 2, 3.
Great. 1, 2, 3. When x is 1, what's y?
6.
When x is 2, what's y?
8.
When x is 3, what's y?
It's not linear.
So 1, 2, 3, 4, 5, 6. 2, 6, 7, 8. 3, oh, I'm off the graph. So 3 takes me off the graph. Do I do this?
Yeah.
No.
That's how I do.
Surprise, surprise. 3 takes me off the graph, so maybe I should try 0, which will stay on the graph. What is 0 times 2?
0.
Plus 4? So I go 0, 1, 2, 3, 4. Does that follow the pattern? Over 1, up 2. Over 1, up 2. Is it linear? Yes. Now check this one. What numbers do you want to use?
Let's use 2, 4, and 6.
2 squared.
4,
Minus 3. 1. 4 squared. Minus 3. 13. 6 squared. 36 minus 3. Is that going to fit on the graph at all? No.
change is not linear because
You know it's not linear, but to graph it, what is a Real smart number we should probably have on every table of values. 0. What's that?
I wanted to mix it up, Mike.
I know that, I'm just saying. Negative 3, right? So 0, 1, 2, 3. 2, 1, 2, 1. 3, I'm off the graph, right? Now, 3 times 3 is, actually I'm not off the graph. 3 times 3 is 9, minus 3 is 6. 1, 2, 3, 4, 5, 6. Everybody cool? And if we do 1, it's negative 2, right? So it makes this nice curve. Now, here's something that's kind of neat. What's negative 1 squared? 1 minus 3? Negative 2. What's negative 2 squared? Minus 3? 1. Negative 1, negative 2. Negative 2, 1. What will negative 3 be without even doing the math? If 3 was 6, if 3 was 6, what will negative 3 be? 6. And it makes this nice half of the curve. This is called a parabola.
Oh no.
You will see them in grade 11. You will see them in physics. You will see them in biology. You will see them in chemistry. You will see them all over the place. They are similar to linear relations because there is indeed a pattern, but it is not a constant pattern because as you can see, it starts getting steeper and steeper and steeper. Everybody understand? That's the basis of calculus, which is where you are heading. Everybody cool? All right, I'm going to stop now because that is it.